Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Concentration polarization. The pressure-driven fluid flow through a selective membrane can effectively transport solute towards the membrane surface. The partially or totally retained solutes will accumulate in a thin layer adjacent to the membrane surface, generating a concentration gradient, that is to say, the solute concentration near the membrane surface is much higher than that of the bulk feed solution. As a consequence, a diffusive flux of solute back to the feed bulk appears. The solute builds up at the membrane surface until the equilibrium between diffusive and convective solute fluxes is attained. As a result, the solute concentration changes from a maximum at the membrane surface to the bulk as illustrated in this figure. This phenomenon, known as concentration polarization. Concentration polarization increases resistance to solvent flow and thus is responsible for the water flux decline observed in many membrane filtration processes. It is strongly related to the osmotic pressure rise, increase of resistance to permeation such as gel formation, and fouling susceptibility. It might also change the membrane separation properties, for instance due to surface charge variations. Concentration polarization cannot be avoided in the membrane process, but it can be minimized by various methods. The extent of concentration polarization can be reduced by promoting good mixing of the bulk feed solution with the solution near the membrane surface. Mixing can be enhanced through membrane module optimization of turbulence promoters, spacer placement, or by simply increasing tangential shear velocity to promote turbulent flow. The prediction of the concentration polarization is required for the design and operation of pressure-driven membrane systems. However, the experimental determination of the solute concentration profiles in the polarization layer still presents many limitations. There are several theoretical approaches investigating the concentration polarization by models: osmotic pressure model, film theory, gel layer model, inertial lift model, and shear-induced diffusion model. It has to be noted that concentration polarization cannot be avoided in the membrane process, but it can be minimized by various methods. Membrane resistance. A schematic overview of the filtration resistances on the membrane surface and inside the membrane has presented. The parameters such as RA, adsorption resistance, RP, pore blockage resistance, RM, membrane resistance, RC, covering layer resistance, and RCP, concentration polarization resistance. The reducing performance of the membrane is based on an increase in the filtration resistance, which increases the output membrane resistance. Concerning the micro and ultrafiltration membrane, the increased covering layer resistance results from adsorption, pore blockage, and covering layer formation itself. The increase of the filtration resistance of the tight nanofiltration and reverse osmosis membranes is due to a concentration polarization of dissolved matter, the concentration of which rises with increasing filtration duration. Increased resistance due to adsorption and pore blockage normally cannot be reduced by measures such as backwashing or the like, so that during severe pore blockage another membrane material should be used. On the other hand, covering layer formation can be decreased by increasing the overflow velocity or backwashing the membrane with permeate in intervals. Fouling and scaling minimization methods. Fouling and scaling can be minimized by strategies such as appropriate membrane selection, choice of operating conditions, pre-treatment system, and membrane cleaning. The first strategy to minimize membrane fouling is the use of the appropriate membrane for a specific operation. The nature of the feed water must first be known, then a membrane that is less prone to fouling when that solution is chosen. For aqueous filtration, a hydrophilic membrane is preferred. Operating conditions during membrane filtration are also vital as they may affect fouling conditions during filtration. For instance, cross-flow filtration is preferred to dead-end filtration because turbulence generated during the filtration entails a thinner deposit layer and therefore minimize fouling, or increasing the overflow velocity in cross-flow operation, covering layer formation can be removed. A good pre-treatment system is essential, but pre-treatment must be backed up by an appropriate cleaning schedule. We will discuss the pre-treatment methods in the next section. In the next slide, I am going to also discuss the membrane cleaning chemicals and factors. Membrane cleaning. If the desired permeate flow is no longer realizable economically, a cleaning plan established by the membrane manufacturer is applied. Membranes can be cleaned physically or chemically or combined. Physical cleaning includes sponges or backwashing in the permeate side or flushing in the feed side. Chemical cleaning uses acids and bases to remove foulants and impurities. It has to be noticed that the specific cleaning procedure is a function of the feed water chemistry, the type of membrane, and the type of fouling. The course of a flow over time at a constant transmembrane pressure with and without chemical cleaning is represented in this figure. Despite the significant improvement of the flow capacity by the chemical cleanings, the flow decreases with increasing filtration time. This phenomenon is explained by irreversible fouling. Cleaning chemicals and factors. The effectiveness of cleaning does not only depend on the cleaning agents applied and their chemical activity, but is also determined by factors such as temperature, pH value, contact or reaction time, the concentration of the active substance, and mechanical forces. For handling the chemical For handling the cleaning chemicals, the references and possible hazards of the respective safety datasheets must be considered. This is of special importance in cases where the personnel are not familiar or only to a limited extent with the use of hazardous materials such as at wastewater treatment plants. Moreover, it has to be considered that some cleaning chemicals, after having been used for cleaning, may have undesirable effects on the permeate quality. After cleaning, these cleaning solutions have to be collected if necessary and disposed of separately. For membrane cleaning, Chemical cleaning agents are used in combination with backwashing in the permeate site or flushing in the feed site. In principle, we distinguish three types of cleaning. First, backwashing or flushing of the membrane. Second, interim cleaning using chemicals in lower concentration. And third, intensive cleaning using chemicals in higher concentration. The cleaning agents used for intensive cleaning have a higher concentration than those used for interim cleaning. The cleaning agent is chosen depending on the substances in the covering layer, as you can see in this table. Depends on the fouling type, cleaning agents are applied. For example, for scaling and colloidal fouling, acids such as citric acid or acetic acid is applied. For organic fouling, anionic surfactants, oxidants such as hydrochloride, hydrogen peroxide, or alkaline cleaning agents such as caustic soda solution. And for biofouling, disinfectants such as hydrochloride or biocides can be applied. Scale control. A good pre-treatment system is essential, but pre-treatment must be backed up by an appropriate cleaning schedule. In fact, scale control is complex, but the particular procedure depends on the composition of the feed water. Calcium carbonate scale, by far the most common problem, is easily controlled by acidifying the feed or by using an ion exchange water softener to exchange calcium for sodium. Alternatively, an anti-scalant chemical such as sodium hexametaphosphate can be added. Because anti-scalant interface with the precipitation of the insoluble cell and maintain the cell in solution even when the solubility limit is exceeded. Polymeric anti-scalants may also be used sometimes in combination with a dispersant to break up any flux that occur. Once the silica scale formed, it is difficult to remove because no effective anti-scalant or dispersant is available. The solubility of silica is a strong function of pH and temperature, but in general, the brine should not exceed 120 ppm silica. Once formed, the silica scale is difficult to remove. Acid cleaning agents such as hydrochloric, phosphoric, or citric acids effectively remove common scaling compounds. With cellulose acetate membranes, the pH of the solution should not go below 2 or else hydrolysis of the membrane will occur. Oxalic acid is particularly effective for removing iron deposits. Exercise. Please complete this table. In this table, the reasons for membrane performance decline has presented. Please fill out the blank and send it to me by course platform or by email. After receiving it, I will send you the response. This is your task. Now, this lecture is up and I will go on with the next section, section 3, pre-treatment and post-treatment. Thank you for your attention.